So Banach spaces, a sequence of vk for k from 1 to infinity v converge to a certain v, a vector of the space, the vector space v, if the norm of v minus uk for k going to infinity is converging to 0. So it means that whatever epsilon, as small as you can find, you can always find a number, an index number n of the integer, where you can dominate the difference in norm between v and uk by epsilon, and this for all k superior to v. So this is the definition of the convergence of a sequence. Okay, so whatever epsilon, as small as you can find, you can always find a natural where a number which for k major than n, you have v minus uk is less than epsilon, and for all k superior to v. So there is some problem here. We need to be able to guess the v in order to use the definition. To demonstrate that the sequence converge, you need to know the limit a priori. So we are going now to define a Cauchy sequence, which is a convergent sequence, and we don't need to know the limit of the sequence anymore. So this is the definition of a Cauchy sequence. A sequence is of vk for k from 1 to infinity in the vector space V is a Cauchy sequence if whatever is epsilon, strictly positive, but epsilon as small as you can find, you could always find a number, an integer, okay, where for all k and n and l integer superior of this n, you can dominate the difference between the term of the sequence vk and vl by epsilon. So this is a Cauchy sequence, and every convergent sequence is a Cauchy sequence. So what does it mean that every convergent sequence is a Cauchy sequence? It only means that it's the same that if you want to determine the limit of a sequence, you can demonstrate first that the sequence is a Cauchy sequence. And by the fact that every convergent sequence is a Cauchy sequence, you will definitely show that your sequence is a convergent one. So definition: a Banach space is a norm vector space in which each Cauchy sequence has, so the vk for k from 1 to infinity converges to some v that belong to the vector space. So the solution to the problem is to restrict our attention to Banach spaces. The good news is that all spaces are mostly spaces in engineering are Banach space. Some examples of Banach space are R, C, the complex number, Rn, the C power n are all Banach space. Theorem. So C from A to B is a Banach space. So the continuous function that operates on a segment between A to B is a Banach space. Proof: let f and this k from 1 to infinity is a Cauchy sequence in the continuous function from A to B. So it means that whatever epsilon, strictly positive, epsilon as small as you want, as you can find, you will always find an integer n, natural, that for an L superior to this n, you can dominate the infinite norm of the difference between two terms of discrete fk and fl by this epsilon. Okay, so we need to show there exists some function f that is defined on the segment AB such that the infinite norm of the difference between f and fl, the infinite norm of the difference between f and fl is converging to 0 for L going to infinity. So the idea is here to use that for x belonging to the segment AB. So we can dominate the difference in the absolute value of AKD of x minus FL of x for whatever x between A and B by the maximum of the difference, the absolute value of the difference FK and the FL for x belonging to this segment. So this maximum is what is known as the infinite norm of FK minus FL. Obviously, the infinite norm is defined on where the function is defined. So, and the function is defined on a segment, which is the segment AB. So, for whatever x, you can always dominate this difference by the infinite norm of the difference of the sequence. Okay? So thus, it means that there always exists an epsilon as small as you want, strictly positive, such that you can always find an integer, an n belonging to n, where the difference between fk and fl in absolute value is dominated by epsilon. And this is true for all k and l superior to n. So this shows that the sequence of complex number, which is the sequence of fk of x, of y of x, for k from 1 to infinity, okay, is a Cauchy sequence in the complex numbers. Since complex numbers C, the corpus C is a Banach space, we could say that the sequence, the fkx for k from 1 to infinity is convergent. But f of x is the limit of fk of x when k is going to infinity. So we need to show that the infinite norm of the difference between f and fl is going to 0 as L is going to infinity, and f belongs to the continuous function on the segment AB. So f is continuous on the segment f is continuous, so f is defined obviously, but more than defined, it's continuous on the segment AB. So to demonstrate this, okay, the star, by letting k going to infinity, we have, because the sequence is convergent, that whatever epsilon strictly positive, as small as you can find, you can always find there always exists a natural number n belonging to n, such that the difference, the absolute difference between fk of x and fl of x is minored by epsilon for L major than n. Okay, this is the definition of the limit. So because the infinite norm of f minus fl is the maximum number for x describing the interval, the segment AB, of the absolute value of the difference between f of x and fl of x is less than epsilon. This is the number, this is the definition of the infinite norm of f, okay, minus fn. So this shows that the infinite norm of f minus fl is going to 0 for L going to infinity. That f belonging to the continuous function of the segment A and B follows the theorem. So recall, C of this notation, C at the power of n, is a collection of sequences. We can say that it's the sequences y, which have the coordinate, first coordinate y, x, y1, x1, x2, xn, where x, k belong to the complex number, k from varying from 1 to n. Now let's consider x, which is x1, x2, x2, x3, an infinite sequence of number where each k belongs to the complex number and k describing the natural number. Let's so define L prime of n, all the sequences that varies from 1 to infinity such that the sum for k from 1 to infinity of the module of xk is convergent. Okay, convergent is less than infinity, so it's a notation. So this is the definition of L1 of n. L1 is respect to the norm that we just defined here, the norm of f1, which is the sum for k from 1 to infinity of the absolute value of xk. So here the space of sequences xk for k from 1 to infinity, for which the sum for k from 1 to infinity of xk is absolutely convergent. So this definition, this sum from k from 1 to infinity of xk is absolutely convergent, is similar, is equal to this mathematical definition here. Okay, so theorem now. L1 of n is a Banach space, which respect to the norm that we just defined, which is the norm of the sequence of xk from k from 1 to infinity, the norm 1. This is the norm 1 of xk. The norm 1 of xk is the sum for k from 1 to infinity of the module of the absolute value of xk. So now the proof. Okay, I just remind you here the inequality of the Cauchy inequality, which is the norm of alpha v, where alpha is a scalar, okay, and v is a vector, a scalar belonging to R, or C is the module of alpha multiplied by the norm of the vectors v, okay, the norm. And we have always the inequality. This inequality is known as the Cauchy-Schwarz inequality. We are going to speak about it later in these lessons. Yes, that the norm of v plus w is less than the norm of v plus u plus the norm of u plus v. I just introduced v minus u plus w. Okay, and we are going to use this inequality to discuss Schwarz inequality. So more generally, let P belong to one infinity. P is a complex. P is an integer. Okay, P can be 1, 2, 3, n, but not real. Okay, P is an integer. Okay, there. So we consider LP of n, which is the sequences, all the sequences, the xk sequences of k from 1 to infinity, such that the sum for k from 1 to infinity of the module of xk at the power p is bounded, okay, is less than infinity. So which means that the series is convergent. Okay, so LP of n is in a way the space of all the convergence series for the p norm. This is the p norm of the sequences that we just defined. Okay, so is this a norm space? This is the question. So how would you like to define a norm space? First, we can say, okay, how can we define a norm space? We can try to put, okay, to say, okay, let's define the norm space as this. Is it work or not? A norm space could be the norm of a sequence xk from k from 1 to infinity. Could be the sum for k from 1 to k of the module of xp at the power p. Could be now, but there is a problem with this Cauchy-Schwarz inequality, because we can't use this Cauchy-Schwarz inequality with this definition of the norm space. Okay, and okay, if we say that, okay, the norm of alpha xk, the sequence alpha xk, where alpha is a scalar, okay, alpha can be real or can be complex, but okay, the sequence of alpha xk from k from 1 to infinity in norm could be, okay, let's say the sum from k from 1 to infinity of the module of alpha xk at the power of p. Okay, which could be, but it's not. We'll see, it doesn't work. That should be the module of alpha p. Okay, we get out from the infinite sum, which will be the sum of alpha of xp for the sum for k from 1 to infinity of the module of xk, of the module, the absolute value of xk at the power p, which should be the module of alpha at the power p multiplied by the norm of the xk sequences. And this is not the right choice for the norm, right? The second guess, and this guess is the right one, is to define the p norm of a xq sequences. Okay, q is muette, it could be xq, it could be in n, but the importance is the p norm. P is important there. So the p norm of the xq sequences is defined, and this is the true definition that you have to remember, as the sum from k from 1 to infinity of the module of xk at the power p and all that sum at the power 1 over p. Okay, so there is a theorem there. So the theorem is that LP of n is a Banach space with respect to this norm. Okay, and so we have the inequality that we can use in the exercise and on Banach space, that the sum from k from 1 to infinity of xk yk is less than the product of the sum from 1 to infinity of the modulo of xk power p power 1 over p by the sum from 1 to infinity of the modulo of yk power p by the power 1p. And this is a fundamental inequality that can help us to solve many problems over Banach space, about limits of sequences, about Cauchy sequences, all that stuff. So this LP norm, okay, has been defined, okay, such as we have this inequality. So because we need this inequality for solving mathematical problems on Banach spaces, okay? So now comes the well-known Minkowski's inequality. So the Minkowski's inequality is true for any p belonging to 1 to infinity, p describing the integer, right? So, and this is the Minkowski's inequality. The sum, okay, for k from 1 to infinity of the absolute value of the sum of xk plus yk at the power of p, the whole at the power 1 over p, is less than the product of two sums. First one is the sum from 1 for k describing 1 to infinity of the absolute value of xk at power p, the whole is power 1 over p, by the sum of for 1 to infinity of the module of xy power p, the whole 1 power p. This is known as the Minkowski inequality, and it's very useful when solving mathematical problems about Banach space, about Cauchy sequences, about series, and all that stuff. And of course, this Minkowski's inequality is respect to the norm, the p norm, okay, of the sequence. And these sequences can be summed up, okay? It's a notation, okay? It's a notation without the infinite summation. But this Minkowski's inequality can be is also known as the p norm of the sequence formed by the sum of xk and yk can be is inferior to the sum of the p norm of the xk sequences and the p norm of the yk sequences. Okay, so this is a fundamental inequalities that we have to keep in mind to solve mathematical problems about series, about Cauchy sequence, about convergence. Okay, so now the linear map T on a vector space V is such that T applied to alpha V plus beta W, where alpha and beta are complex number and V and W are belonging to our vector space, is equal to alpha T of V, okay, plus beta by T of W, okay, and this for V and W belonging to our vector space, whatever alpha, whatever beta belonging to the complex number. So it's alpha T of V plus beta T of W, okay? So now comes the very important definition. A linear map T, okay, is an application that take a vector from a vector space V and give vector from vector space V is bounded. Okay, this is the definition of a linear map that is bounded if and only if you can always find a K, case positive obviously, where the norm of TV applied to your linear map applied to whatever vector V in the V space is less than K. K is a scalar here, real. Okay, of course, multiplied by the norm of this vector V. And this is true whatever V in our vector space. So you can always find a K such that you have this inequality whatever the vector of your vector space. And this is the definition of a linear map which is bounded. And we have to keep in mind this definition, and we have to know it by heart, obviously, in the exercise. Okay, the summary possible value of k is denoted in the norm of k. Both this is not very important. Call the operator norm of t. Okay. There can be, okay. There is also okay, some inequality. We have the two norm of tv is less than kf by the norm 1 of v. Okay. Some example. So let's consider a linear map. Okay, a linear map. We'll see. T that goes from the continuous space from 0 to 2 to the continuous space from 0 to 2, such as Tf of y is equal to y at the power of 2 f of y. F of y. We would like to show that first T is well defined, and it actually maps C02 into C of 02. Okay, we would like to show then two that T is linear. Okay, and we would like to show that T is bounded. Okay, so let's prove that. So the first is satisfied. Why? Because x at the power of 2 f of x is a continuous function on the segment 0, 2, and it goes to the segment 0, 2. Okay, it's a continuous function as a product of continuous function. F is continuous, x2 is continuous. Okay, so this would break down if we had, for example, tf of x will be 1 over x by f of x, because this linear form is not defined in 0. Okay, or here 0 is included in the segment. Okay, you see that, I hope so. So for tf of x will be 1 over x f of x. Tf does not belong to the continuous segment 0, 2. Okay, then let's prove 2 that t is linear. Okay, we have t of alpha f plus beta g is alpha tf plus beta tg as an easy calculus. Then let's demonstrate that t, this application, is bounded. Okay, I recall you, so is bounded. So what does it mean? It means that we can find a k integer such that the infinite norm of tf is less than k by the infinite norm of f. Okay, but I recall you that the infinite norm of the operator t is defined as the maximum number of t f of x for x describing our interval, which is ab. Okay, so we have the absolute number of tf of x is the absolute number of x power of 2 f of x, which is x power of 2 by the absolute number of f of x. And because x belonging to 0 and 2, we can measure this quantity, because x is always inferior of 2, so x2 is always inferior of 4. So we can measure minus this quantity by 4 by the infinite norm of f. So that we just demonstrate that the infinite norm of t of f which is equal by definition of the maximum number of tf of x of y for y describing the interval 0 of 2 is less than 4 by the infinite norm of f. Okay, so we observe that t is less than 4. Okay, and we find our k is equal to 4. Okay, so we demonstrate what we wanted. So let's take a second example. Okay, so let's consider the linear map T, okay, which goes from LP of n to LP of n. Okay, so which apply to a sequence. Okay, let's define this linear map that apply to a sequence xk for k from 1 to infinity give us, okay, a new sequence, okay, which is formed by xk and xk plus 1 for k from 1 to infinity. Okay, so to visualize what these operators, how this operator act, okay, on our sequences, we have that t of xy, x2, x3, okay, is the vector which are for first coordinate xy plus x2, for second coordinate x2 plus x3, for third coordinate x3 plus x4, etc., etc. Okay, so we see that t is well defined. Indeed, t of sequence x can belong to LP of n if x, the sequence x itself, of course, belong to LP of n. Then t is linear, and then t is bounded. So let's prove then that for the first, in the first order, let's xk belonging to LP of n. Then we are interested in the norm of t of xk, the p norm of that. Okay, so we use the Minkowski inequality, and we have that the sum for k from 1 to infinity of xk in absolute value plus xp plus xk plus 1, it's not a p, it's a k, at the power of p, the wall at the power 1 over p is less than the sum for k from 1 to infinity of the module of xk, the power of p, the wall is power 1 over p, plus, no, it's a multiplication here, what I say, okay, the sum for k from 1 to infinity of xk. Okay, so this is equal to this. Okay, and the sum for k from 0 to infinity of xp over 1 over p plus the sum for k from 2 to infinity of the module of xk of the power p 1 over p is less than 2 times this module. Okay, we just change, you know, the indices. Here we start from 1, and here we start from 2. Okay, so, and this is less than infinity because the sequence xk belong to LP of n. Then we just demonstrate, we just prove that the operator t acting on the sequence of xk belonging to LP of n as desired. For the third, you can do it. Okay, it's that it's bounded. I'll let you work a little bit. Okay, the argument in one shows that, okay, shows that the p norm of t acting on the sequence xk is less than 2 by the p norm of the sequence xk, whatever the sequence xk belonging to LP of n. So t is bounded, and the norm of t is less than 2. Okay, this is the first video of a wide series I will do on the subject. I hope you enjoy it, even if it's in English, and my English is really, really shit. Okay.